tremendous flash. It's like 1,000 lightning at the same time.
Fire is coming down from the top of the window.
Many things flying over our body.
In our universe, there are two ways to unleash the energy inside an atom: split a heavy atom apart or fuse two light atoms together. These processes, fission and fusion, are the engines behind the atomic bomb and the hydrogen bomb. Fission splits atoms, powering the A-bomb. Fusion joins them, powering the H-bomb. The difference isn't just technical, it's the difference between city-level destruction and global catastrophe. Einstein's E=mc2 revealed that a tiny bit of mass can become immense energy.
The equation E is equal mc squared showed that very small amount of mass may be converted into a very large amount of energy.
Which means with only this much material, you can destroy a city.
A short time ago, an American airplane dropped one bomb on Hiroshima. That bomb has more power than 20,000 tons of TNT,
setting humanity on a dangerous new path. The A-bomb, born from fission, was once thought to be the ultimate weapon, until scientists learned to ignite fusion, the reaction that powers the stars. The H-bomb uses a fission bomb as a trigger, unleashing a force that makes the A-bomb look small by comparison. In today's world, as nuclear tensions rise, understanding this difference is crucial. It's the line between a regional disaster and an existential threat. The atomic bomb works by splitting large, unstable atoms like uranium-235 or plutonium-239. A single neutron strikes the nucleus, causing it to split and release energy plus more neutrons, which trigger further splits in a chain reaction. This cascade happens in less than a millionth of a second, unleashing a massive explosion. To achieve this, enough fissile material must be packed together what's called a critical mass. Hiroshima's little boy used uranium. Nagasaki's fat man used plutonium. The bomb's design rapidly brings subcritical material together, either by firing one piece into another or by imploding a sphere with explosives. The result, a blinding flash, a wave of heat, and a blast that flattens everything nearby. Hiroshima and Nagasaki's bombs yielded 15 and 20 kilotons, enough to destroy cities, but only the beginning. Fission bombs are limited by how much fissile material can be safely assembled. But this limit would soon be shattered by fusion. Fusion is the process of forcing light atomic nuclei, like deuterium and tritium, to merge into a heavier nucleus, releasing enormous energy. This is the reaction that powers the sun, where hydrogen atoms fuse under immense heat and pressure. In a hydrogen bomb, fusion fuel is ignited by the heat of a fission bomb. The fusion of deuterium and tritium produces helium, a neutron, and a burst of energy. Pound for pound, much more than fission. The challenge is overcoming the natural repulsion between atomic nuclei, requiring temperatures of millions of degrees. Only a fission bomb can create these conditions on Earth. Thus, an H-bomb is a two-stage device. A fission bomb triggers a fusion explosion. This makes H-bombs far more complex and vastly more powerful than A-bombs. The yield of a fusion bomb is limited mainly by how much fusion fuel it contains. That's why H-bombs can threaten entire regions, not just cities. The breakthrough that ultimately made the hydrogen bomb possible and reshaped the landscape of nuclear weaponry is the ingenious Teller-Ulam design, a sophisticated two-stage mechanism that revolutionized thermonuclear weapon design. This innovative approach allowed for significantly higher yields compared to previous designs. The bomb contains a primary fission stage acting as the trigger for the much larger fusion reaction, and a secondary fusion stage containing the fuel that will unleash the bulk of the weapon's energy. When the primary explodes, it emits a burst of incredibly intense X-rays, which are precisely channeled and focused onto the secondary stage. These X-rays rapidly heat and compress the secondary's fusion fuel, lithium deuteride, a compound crucial for the fusion process. Using a process known as radiation implosion, squeezing the fuel to immense densities. At the very core of the secondary stage is a plutonium spark plug, a small fissile core, which undergoes fission under the extreme pressure, initiating a chain reaction. This fission provides the intense heat necessary to ignite the fusion reaction in the surrounding fuel. The fusion reaction then releases an exponentially greater amount of energy, as deuterium and tritium isotopes of hydrogen combine in a thermonuclear inferno. Fast neutrons, byproducts of the fusion reaction, bombard the lithium in the lithium deuteride, creating even more tritium, thus fueling further fusion reactions and boosting the overall yield. Some advanced designs wrap the entire device in a jacket of uranium-238, which itself undergoes fission when struck by the high-energy fusion neutrons, adding yet another layer of explosive power, but also significantly increasing the amount of radioactive fallout. This complex fission-fusion-fission sequence is what allows hydrogen bombs to maximize their destructive yield. The entire process, from the initial fission explosion to the final fusion burst, unfolds in mere microseconds. It's a chain reaction of cascading explosions, with each stage amplifying the energy released by the previous one. The result is a weapon possessing almost unimaginable destructive potential, capable of leveling entire cities. The H-bomb's design stands as a chilling masterclass in using the energy from one precisely controlled explosion to trigger an even larger one, with each successive stage releasing exponentially more power than the last, creating an escalating cascade of destruction. This is precisely what makes thermonuclear weapons such a terrifying and destabilizing force in the modern world. The difference between A-bombs and H-bombs is best understood by their yields. A-bombs are measured in kilotons, thousands of tons of TNT. Hiroshima's bomb, 15 kilotons. H-bombs are measured in megatons, millions of tons of TNT. The first H-bomb test, over 10 megatons. That's nearly 700 times more powerful than Hiroshima. A 20 kiloton A-bomb can destroy a city's core. A 20 megaton H-bomb can obliterate an entire metropolitan area. The destructive radius grows dramatically with yield, turning city killers into region destroyers. Fission bombs are limited by critical mass. Fusion bombs are limited only by how much fuel you add. H-bombs can be built to any size, from hundreds of kilotons to tens of megatons. This scalability is what makes the H-bomb the ultimate weapon of mass destruction. It's not just more powerful, it's a leap to a new scale of devastation. When we talk about the most destructive forces ever unleashed by humankind, one weapon stands above all others. That weapon was the Soviet Union's Tsar bomber, detonated in 1961. It remains the most powerful nuclear device ever exploded. Originally designed for a staggering 100 megatons, the Tsar bomber's yield was intentionally reduced to 50 megatons for its test. Even at half its potential, it was still the largest explosion ever created by human hands, a record that still stands today. To put its power into perspective, that's approximately 3,300 times more powerful than the atomic bomb dropped on Hiroshima. A truly terrifying comparison. The initial fireball generated by the explosion was a monstrous 5 miles wide, incinerating everything within its reach. The resulting mushroom cloud ascended an astonishing 40 miles into the atmosphere, reaching far into the stratosphere. The force of the blast was so immense that it completely leveled villages within a 34-mile radius of the epicenter. The shockwave from the explosion traveled vast distances, shattering windows in buildings hundreds of miles from ground zero. It was estimated that third-degree burns would have been possible for anyone within a staggering 60-mile radius of the blast. The sheer size and destructive power of the Tsar bomber made it an impractical weapon for actual warfare scenarios. Instead, its primary purpose was to serve as a demonstration of Soviet technological and military might during the Cold War. Experts calculated that had the bomb been detonated at ground level, the resulting nuclear fallout would have contaminated thousands of square miles, rendering the area uninhabitable for generations. The Tsar bomber served as a stark reminder that hydrogen bombs are not simply scaled-up versions of atomic bombs. They represent a quantum leap in destructive capability, transforming warfare into a matter of planetary consequence. The test forced the world to confront the terrifying possibility of nuclear winter and the potential for human extinction. The legacy of the Tsar bomber serves as a chilling reminder of the immense destructive power that we, as humans, have managed to unlock. It stands as a stark warning of what could happen if the energy of a star is ever fully unleashed upon our planet. The difference between fission and fusion bombs is at the heart of today's nuclear crisis. Iran's uranium enrichment raises fears it could build a fission bomb, shifting the balance of power in the Middle East. Even a simple A-bomb could devastate a city like Tel Aviv and trigger a regional arms race. The deeper fear is that mastery of fission could lead to thermonuclear weapons. H-bombs would make Iran not just a regional threat, but a global one. The leap from A-bomb to H-bomb is significant but well known. A state with a few fission bombs is dangerous. A state with H-bombs is an existential risk. That's why international monitoring focuses not just on fissile material, but on signs of advanced thermonuclear programs. The stakes are the difference between holding a city hostage and holding the world hostage. How do we know when a country tests a nuclear weapon? A global network of sensors constantly monitors for nuclear detonations. Seismic stations detect the shock waves from underground explosions, distinguishing them from earthquakes. The CTBTO's international monitoring system triangulates the location and estimates the yield of any blast. Radioactive gases like xenon isotopes can escape into the atmosphere after a test, providing further evidence. Fusion tests are harder to confirm, but their massive yields and unique isotopic signatures give them away. A test in the hundreds of kilotons or megatons is almost certainly a thermonuclear device. This global detection system is a crucial tool for nuclear non-proliferation. It's our scientific safeguard against secret development of world-ending weapons. The leap from fission to fusion marks not just a technological advancement, but a profound turning point in human history, altering the very stakes of global conflict. It represents a shift in scale, a difference not just of degree but of existential proportions. The A-bomb can destroy a city. Its impact, while devastating, is geographically contained. The H-bomb, on the other hand, possesses the potential to threaten civilization itself, casting a shadow over the entire planet. Its destructive capacity is almost unimaginable. Fission's power is finite, measured in kilotons, representing a specific, albeit terrifying, amount of energy. Fusion's is scalable, measured in megatons, meaning there's virtually no upper limit to the devastation it can unleash. The H-bomb uses the A-bomb's city-ending force as a mere trigger, an igniter for a much greater explosion, a cataclysmic event dwarfing anything seen before. This is the technology behind mutually assured destruction, the chilling concept. The logic that's kept the world in uneasy peace, a precarious balance built on the threat of annihilation. The difference between fission and fusion is why the world watches nuclear programs with such anxiety, scrutinizing every development, fearing the potential for escalation. A fission bomb is a crisis, a localized catastrophe. A thermonuclear arsenal is a potential endgame for humanity, a threat to our very existence. International monitoring is one of our few safeguards against crossing this line in secret, a vital mechanism for preventing the unthinkable. The story of A-bomb versus H-bomb is about thresholds, critical junctures in history. First, entering the nuclear age, unlocking the power of the atom. Second, the far more dangerous leap to fusion, a step that forever altered the landscape of global security. Understanding this isn't alarmism, it's realism, a clear-eyed assessment of the world we inhabit. The power to split and fuse the atom is humanity's greatest responsibility, a burden we must bear with utmost care. Our future depends on the wisdom to control it, to harness its potential for good while averting its catastrophic misuse.